Hello, welcome back to our discussion on the differential amplifiers. And this time we are going to simulate the behavior of this circuit with respect to the common mode signals. So as you can see on your screen, I have this differential amplifier Q1 and Q2 with their collector resistors and the emitter resistor. One single, this is called as tail. This acts as a current tail, and to the inputs at the base pins of these transistors, I am applying a signal common to both the inputs. So I am using a sinusoidal signal here that has a DC offset of 0.7 volt, which will help me to bias these transistors. Then I'm using the 10 millivolt peak signals or 20 millivolt peak to peak at the frequency of 1 kilohertz. And I'm using the 10 cycles to run. The sinusoidal signals will be 10 cycles like this, up to 10. And I am going to run the transient analysis for this signal, which is starting from 0 second. It will run up to 10 milliseconds to capture the signal of about 1 kilohertz. And the steps would be from 0 to 10 millisecond. At every 1 millisecond, it will plot me a data. What I am going to show you, if I am applying a signal common to both the inputs of the differential amplifier. For example, here, the two inputs are there shorted, and I am applying a common signal, V in, and the output would be gain times VID. So since the signals at the V1 and V2 are same, the difference VID is 0, therefore ideally I should have 0 output at the output terminals, and that's what precisely we are going to do. Now let us run that analysis. So again, I would like to show you how I apply this sinusoidal source. I right click here and you can see I have a DC offset of 0.7 volt that provides the bias point to the circuit. So 0.7 volt is applied to the base pins of both the transistors. So obviously that DC offset will also get cancelled because the difference between these two will be 0. And I am applying then the time varying signal of 10 millivolt peak, and then at a frequency of 1 kilohertz, and number of cycles are 10. And I will click OK. Then let me show you the transient analysis by right clicking the mouse button or keypad. Here I see the transient behavior of the circuit, where stop time is 10 millisecond and time to start saving the data is 0 millisecond. Maximum time states I'm using 1 millisecond. And that's how once I put the parameters, I get the syntax for the spice command dot trans 0 to 10 millisecond up to 1 millisecond. Once that is done, what I'll do here, I will click the run button to plot my signals. So I am interested in the input signal. So let us simulate this waveform. Here I see the first signal I can do on the schematic. I should have this probe here, the red probe, and on your screen to the left bottom, extreme left bottom C, I'm prompted to click the probe button to plot the voltage at VB1 or VB2 right here. Okay. And because I have applied the signal common to both the base of the transistors. And the DC operating point of this pin is 699 millivolt. That is about 0.7 volt, which I have applied externally. So let us click here, and you see here the 10 millivolt signal riding over the 700 millivolt DC bias point, and therefore the maximum value of the signal is 710, minimum value is 690 millivolt, and I'm having a pure sine wave. Now this signal could be noise also with such a magnitude, that is coupling simultaneously both the inputs of the transistors. And that's what the beauty of the differential amplifier. It helps us to reject or eliminate the common mode signals, which are noise or let's say a DC level from the preceding circuits, etc. Now what I'll do, I will plot the VO1, that is the output of the collector pin voltage at the transistor Q1, which is my output 1. and here I go. So I would add the plot pane by right clicking here, and I would say VB1 or even the VB1 or VB2, they are same, right? See here the labeling VB1 and VB2 because that's the common signal as input. Now VO1 is the blue one which I just plotted here, and the DC operating point or the DC level of this signal is about 1.51, and on top of that my signal is getting there. So you see here I have like let me see again, 1.516. That's my level. And if I see how much is the peak value, just zooming. So 1.516, and here I reach a maximum 1.510. So it's about uh, zero point 0.5 millivolt or something like that. Well, it's about 500 millivolt. Yeah, 500 millivolts. So zoom in, but this is the single ended output. Let me remind you, we are interested about differential output. So what I'll do now, I'll click the VO2 here. So VO2 is right here. Let me just do that. I go to schematic, and I see here I have then plotted the VO2 also, which has the same, and the phase of the signals are also same. But the output is phase inverted with respect to input, but VO1 and VO2 has the same phase, which is expected because the signal is common to both the inputs. Now, this is my single-ended output if I want that. So it is not a differential amplifier. I want to obtain the output for the differential amplifier. So I will just right click the keypad and then add plot pane. And again, here I have like VB2 here, and then VO1 and VO2 can be plotted on this one. I'm just shifting those signals. And now on the empty pane, I right click add trace, and I will plot the difference between the two outputs, which is VO1 minus VO2. And you see the difference is now plotted, which is obviously, since VO1 and VO2 are of same magnitude, I am getting 0 volt at the output. So you see, for applied common mode signal, I am getting a 0 output. So no output is there. So that's the beauty of differencing, uh, taking the differential output of the circuit. So this topology can be applied to other circuit innovations also. So hope you found this video useful. If you did so, subscribe to the channel, click the like button, share it with others, and stay tuned. Till then, wish you happy learning.